We looked at the combination formula in class yesterday. Just know that the combination formula can be represented this way, or like this, as it is in the binomial probability formula for AP Stat. So it might be a situation like, hey, if we have 8 things, find the number of ways that you could get 3 successes, 3 of them selected to be successes out of 8. Well, recall we said that you take 8 factorial and then divide it by 8 minus the number of successes, which would be 5 failures, and 3 successes, and that would be it. That would be how you would find the number of combinations. We can go back and look at the notes from the other day for more of an explanation of that, but I just want to remind ourselves that that's how we get the number of combinations. You know you're looking at a binomial probability situation, a binomial setting, if these 4 things are true, that you can stipulate something as either a success or a failure. Like if you're rolling a die, you could say that rolling a 5 is a success, rolling any other number is a failure. So even though there were 6 possible outcomes, we'd say that rolling the 5 was the success and then all the other numbers are failures. N is the number of trials, so it's like how many times are we going to roll the die. It has to be fixed, so going into the problem we say, hey, we're going to roll the die 9 times or 10 times or whatever. So it's got to be fixed in the problem. The trials are independent, so each roll doesn't affect the roll before it or the roll after it. And because they're independent, the probability of success is locked in, it never changes. So for example, our probability of rolling a 5 would be 1/6. It never changes from roll to roll. Okay, so we're going to have these binomial probability distributions. We've seen these before. Now the random variable x is going to keep track of the number of successes in n trials. So let's suppose we had 6 trials, like we'll roll a die 6 times or whatever. Then this would be our distribution. We have anywhere from getting no 5s in 6 rolls to 1 time we got a success, we rolled a 5 in the 6 rolls or whatever. So that's what that is. We're going to need a success rate so we can calculate these probabilities. And it's these probabilities we want to calculate in a binomial setting. So our success rate could be, hey, you got a 1/6 chance of rolling a 5. Or there might be a problem that says, hey, 65% of voters approve of this initiative or whatever. So we'll be given a success rate and we'll be able to find the probabilities. Oh, this is sad. I don't know how this beautiful picture of these 2 horses got placed here, but had a buddy that had 2 horses lately. They were amazing racers. They were so close. They called them peanut butter and jelly. But eventually peanut butter and jelly got old, kind of put them out to pasture. And then eventually the 2, you know what happens with old horses, and they become dog food, but I don't know how that slide got in there. Anyway, here we go. Let's suppose that 72% of Americans like peanut butter and jelly sandwiches. Oh, that's messed up. That's disrespectful. But okay, if we randomly select 9 Americans, find a probability that 5 of them are going to like peanut butter and jelly sandwiches. So we're going to build this probability distribution down here. We can have anywhere from 0 through 9 successes. So out of the 9 people, maybe none of them like peanut butter and jelly sandwiches. Maybe all 9 of them do. Then what we have is we can represent a binomial distribution with its 2 parameters, how many things are going to be selected and what's its success rate. So for us right now, we're going to select 9 people, and we were told in the problem that there's a 72% success rate. So we use this information to find the probabilities. This is the binomial probability formula that AP Stat gives us on the formula sheets when we take the exams. This is the combination formula. So here's how it works. We are trying to find the probability of getting 5 people out of 9 that like peanut butter and jelly sandwiches. So we are trying to find this probability right here associated with getting 5 successes when x is equal to 5. To find that, we take a combination of 9 choose 5 times our 5 success probabilities times our 4 failure probabilities, and that will give us our answer. AP would like you to show what this combination means in terms of factorials, so we'll get used to putting that down. And then what we can do is we can go to the binomial PDF function on our calculator and type in n, p, and x in alphabetical order. So if we go there, if we go to the calculator, we're going to find the binomial PDF function, the same place where we find the normal CDF function, which is above ours under distribution. So we'll go second distribution. We can scroll up till we get to binomial PDF. We're going to learn about binomial CDF soon, but for now just PDF, because it stands for probability density function. So we type in, we have 9 people. Out of those 9 people, we're looking at a probability that they like peanut butter and jelly sandwiches at 0.72. and we want to find the probability that we get 5 people out of the 9 that like peanut butter and jelly sandwiches. So we paste it. This is how it should look on the older calculators, N, P, and X in alphabetical order. And then we find, oh, our probability is 0.1499. So we would bit ado to the calculator, and we would go over here, and this was whatever we just said, 0.14599 or whatever. So we found our probability, and this is how we show our work, but this is really how we're practically going to actually get that probability. Now, a couple of things here, and this is important. Let's suppose we got 9 people, and their order doesn't matter. They're just scattered all over the place. But here's how this works. It'd be nice to understand this formula. And what we're saying is, what's the probability that exactly 5 of these people prefer the, or like peanut butter and jelly sandwiches? So we need to find what's likely that exactly 5 like them. Well, it could be this one, this one, this one, and this one, and this one. Those could be the 5 people that like the peanut butter and jelly sandwiches. What was the probability that this person liked it? 0.72. And this person liked it? 0.72. And this person liked it? 0.72. And the other one, 0.72. And the fifth one, 0.72. But then we'd also have to have 4 people that don't like it. If there's a 72% chance that a person does like peanut butter and jelly sandwiches, then there's a 0.28 chance that they don't. And there would be 4 of those people. So 0.28 times 0.28 times 0.28. That's 4 people. So we could raise that to the 4th power. In fact, we can see that this becomes the calculation for the probability of any one combination of 5 people out of the 9 liking peanut butter and jelly sandwiches. The probability that 5 of them would like peanut butter and jelly sandwiches is this, and the other 4 would be 0.28 to the 4th. So this part of the formula finds the probability that any one combination of 5 people out of 9 would like the peanut butter and jelly sandwiches. But look, it doesn't have to be this person, this one, this one, this one, and this one. It could be, for example, okay, this person and this person like them, and this one, and this one, and this one. Now that's a different group of 5, but we would still have 5 people that like them and 4 that don't. So the probability would still be this, the likelihood of that happening. So it would still be this guy right here. Hence, why is it that we multiply by the combination formula? This counts the number of ways that you can end up with 5 different people liking the peanut butter and jelly sandwiches out of a group of 9. So this counts the ways it can happen. You just multiply that by each way's separate probability, which they're all the same, 5 successes and 4 failures. That's what this formula is doing. And then, now we can use the binomial probability formula on our calculator to do that. One last problem. Let's say weights of bags of flour are normally distributed with a mean of 5.1 pounds and a standard deviation of 0.15 pounds. If we select one bag at random, find the probability that the weight exceeds 5 pounds. Now remember what we used to do? We'd say, hey, let's draw the normal curve. Let's put the mean of 5.1 here. We're going to go down here and find where exactly 5 pounds is, and we find the area above that. So it's good for us to picture a normal distribution to get a feel for the probability that we're going to find. Turns out if we use normal CDF or whatever, this is that probability right there. Okay, now, the problem might proceed now, it might progress. Given that information that there's a 74.75% chance of getting any one bag that exceeds a weight of 5 pounds, what if we randomly selected 7 bags? Now let's find the probability of that. Okay, now in the past, we've done a problem. We can say, what's the probability that the mean in that sample exceeded 5 pounds? In that case, we would go to a sampling distribution of means. We'd change the standard deviation by taking the old standard deviation, dividing it by radical end, and we'd be off and running. But now we have a new possibility. Instead, it could say, okay, given that that's our probability, any one bag at a time exceeds 5 pounds, now if we randomly select 7 bags, what's the probability that 4 of the bags exceed 5 pounds? Well, this is a binomial problem because n is fixed, the number of trials. Each bag has a 0.7475% chance of exceeding 5 pounds, and this is our x. X is equal to 4. That's the number of successes for which we want to find a probability. So we say, okay, we're dealing with the binomial probability distribution, where this is the number of trials, and that's our success rate. That's the likelihood of getting any one bag that weighs more than 5 pounds. And we appeal to the binomial probability formula, and we say, oh, okay, oh, now by the way, I think it's a good idea to at least visualize this. Just like it's a good idea to draw a normal curve when we're visualizing where our probabilities are for a normal distribution, it's a good idea to stop and think, oh, you know what? We've got this binomial probability distribution where the number of successes could be anywhere from 0 through 7, and we're going to try to find the probability that we get exactly 4 successes. So that's this. We want to find this probability down here that we get exactly 4 successes. So we follow the formula, and the formula would say, well, let's skip the combination thing for just a second. Let's do this logically. The probability that any one bag would exceed 5 pounds would be 0.475. We need 4 of those bags to exceed, and out of our sample of 7, we need 3 of those to not exceed that many pounds. Now, if this is the probability of success, 1 minus this is 0.2525. So this would be the probability that that we would get, like, the first 4 bags were heavy and the next 3 were not, but that's only one scenario. So we need to multiply this one probability by this guy, 7 factorial over 7 minus 4, which is 3 factorial times 4 factorial, because this will count the number of ways that this can happen. For every one way we get 4 bags that are successes, this would be the probability, but we have to multiply it by that many scenarios right there. So that's what we write down, and then we go to the binomial PDF on the calculator, and we would get our answer to that problem, and it comes out to be 0.1759. So that would be our probability, 0.1759 chance that 4 out of the 7 bags would exceed 5 pounds.